Have you ever found yourself in, say, a bustling coffee shop, or maybe just navigating a crowded city street, and effortlessly, almost magically, you pinpoint exactly where that conversation or that sudden car horn came from? It's really a remarkable feat our brains accomplish every second, often without us even realizing the intricate calculations happening behind the scenes. But what if we could teach machines to do the exact same thing, with the same accuracy, the same robustness, maybe even surpass our own capabilities? Today, we're taking a deep dive into the fascinating, intricate, and, well, genuinely groundbreaking world of biologically inspired sound localization. We're unpacking a truly innovative paper that unveils a silicon cochlea pair, an incredible piece of engineering designed to mimic the very ears and brains that allow us to locate sound with such precision.
That's absolutely right. Our source for this deep dive is an article titled A Biologically Inspired Sound Localization System Using a Silicon Cochlea Pair. It details how a team of researchers has gone right back to nature's drawing board, looking at the blueprint of human hearing, to build systems that can learn to locate sound sources in some pretty complex, real-world environments. It's really a testament to the power of biomimicry in engineering.
Right, so our mission in this deep dive is clear. We want to unpack every layer of this innovative system. We'll explore how it works, what exactly makes it biologically inspired, beyond just a catchy phrase, how it performs against the gold standard human hearing itself, and what genuinely incredible doors it opens for the future. Things like robotics, smarter hearing aids. So get ready for some truly profound aha moments, because honestly, what they've achieved here sounds nothing short of revolutionary.
It really is exciting stuff.
So let's start with the original masterpiece, the marvel that is the human auditory system. Forget the machines for a moment. How do we as humans so accurately pinpoint a sound's origin without consciously calculating anything? It's all happening behind the scenes, right?
It's an incredible testament to millions of years of evolution, truly. Our ability to localize sound isn't just about hearing, it's about incredibly sophisticated neural processing. And at its heart lies what's known as the duplex theory of sound localization, a really foundational concept proposed by Lord Rayleigh, a British physicist, way back in 1907. He basically figured out that our brains primarily use two distinct cues, which are constantly being processed in parallel.
Two cues. Okay, what are they?
Well, the first, and maybe the most intuitive one, is the interaural time difference, or ITD. Simply put, this is the tiny, almost imperceptible difference in the time a sound wave arrives at one ear versus the other. Imagine a car honking directly to your left. That sound wave will hit your left ear just a minuscule fraction of a second before it reaches your right ear. And our brain is exquisitely sensitive to these tiny differences, nanoseconds, really.
Wow, nanoseconds.
Exactly. And this cue, the ITD, is particularly crucial for localizing low-frequency sounds, generally those below about 2 to 3 kilohertz.
Why low frequencies specifically?
That's the fascinating part. At these lower frequencies, the sound wave's length is actually larger than the size of your head. So the sound wave can effectively wrap around your head without being significantly blocked. This makes the time difference a very clear and reliable indicator of direction for those lower sounds.
It's like a finely tuned stopwatch built right into our skull.
Pretty much, yeah.
Okay, so our brains are timing the sound arrival, like a natural sonar system. What's the other crucial cue then?
The second cue, equally vital, is the interaural level difference, or ILD, sometimes called interaural intensity difference, IID. This refers to the difference in intensity or perceived loudness of a sound at each ear. Now, this cue comes into play mostly for higher frequencies, typically above that 2 to 3 kilohertz mark.
Okay, so higher frequencies behave differently.
They do. Because these higher frequency sound waves have shorter wavelengths, they're much more easily blocked or attenuated, meaning made quieter as they try to pass through your head to the far ear. Your head basically casts an acoustic shadow.
An acoustic shadow, I like that.
So if that same car honks to your left, the sound will be noticeably louder in your left ear than in your right, because the head blocks some of the sound energy from reaching the right ear. This difference in loudness provides another critical piece of information for our brains to localize the sound, especially for those sharp, high-pitched noises.
Okay, let's really unpack this. So our brains aren't just passively receiving sound. They're running these incredibly sophisticated real-time comparisons of both arrival times and loudness levels between our two ears, all happening unconsciously. It's a dynamic, multifaceted calculation, constantly adapting based on the sound's frequency. That's truly mind-boggling when you stop and think about it.
Absolutely. And if we connect this to the actual biological pathway, the complexity only deepens. It's not simple. These binaural signals, packed with ITD and ILD information, aren't just immediately perceived. First, they undergo this remarkable pre-processing in the cochlea, that tiny spiral-shaped cavity in your inner ear.
Probably the snail shell thing.
Exactly. The cochlea acts like a frequency analyzer. It breaks down complex sounds into their constituent frequencies, much like a prism separates light into colors. From there, these finely tuned signals are converted into electrical neural impulses in the auditory nerve. These impulses then embark on this lightning-fast journey, traveling through the cochlear nucleus, or CN, in the brainstem, before arriving at a truly critical hub, the superior olivary complex, or SOC.
The SOC, okay.
This is where the real magic of ITD and ILD processing gets coordinated at a neural level. It's a major processing center.
So the SOC is like the grand central station for sound localization in our brainstem.
Yeah.
How does it handle these two different types of cues? The timing and the loudness differences, is it in separate departments or something?
You could almost think of it that way, yeah. It's a highly specialized processing center. Within the SOC, two specific nuclei are believed to be specialized for each cue. The medial superior olive, or MSO, is thought to be the primary encoder for those minute ITD cues we discussed.
The timing differences.
Right. Its neurons are essentially sophisticated coincidence detectors. They receive excitatory signals that tell them to fire from both sides of the brainstem. An MSO neuron will fire most strongly only when the signals from both ears arrive at precisely the right time relative to each other, meaning when the time difference perfectly aligns with that neuron's specific built-in delay sensitivity.
So each neuron is tuned to a specific tiny time difference.
That's the leading theory, yes. It's a beautifully precise mechanism for measuring time differences across different frequency bands. In parallel, you have the lateral superior olive, or LSO. This is believed to encode the ILD cues, the loudness differences.
Okay, how does that work? Is it just measuring loudness?
It's a bit more complex. Unlike the MSO, the LSO operates on this fascinating push-pull mechanism. It receives both excitation and inhibition. It gets excitatory signals directly from the same side, the ipsilateral cochlear nucleus, but crucially, it also receives inhibitory signals telling it not to fire from the opposite side, the contralateral cochlear nucleus, relayed through a group of inhibitory neurons.
So same side excites, opposite side inhibits.
Exactly. This creates a powerful contrast detector. The stronger the sound on one side, the more excitation. The weaker the sound on the other, the less inhibition is overcome. This makes the LSO neurons exquisitely sensitive to interaural level differences.
So it's not just detecting loudness. It's actively comparing loudness using excitation and inhibition, sharpening the directional signal. Wow.
Precisely. It's a really elegant computational strategy implemented in biology.
Okay, here's where it gets really interesting and frankly a bit mind-bending for me. If nature has honed such an elegant, robust, and incredibly efficient solution over millions of years, why wouldn't engineers try to mimic it? But I can only imagine the monumental challenges. Trying to build something based on this incredibly complex biological process?
Seems like
Well, like trying to bottle lightning.
you've absolutely hit on the core challenge. Mimicking this natural robustness is the holy grail, really, for neuromorphic engineers. Early pioneers in the field, people like Carver Mead, recognized the elegance of the biological design and began exploring these concepts computationally. You had folks like R.F. Lyon back in 1983 proposing early computational models, focusing on cross-correlation between cochlear models. Then there were models incorporating the Jeffress delay line concept from 1948, which is basically a theoretical neural circuit designed to detect time differences by comparing signals along paths of different lengths.
So people have been trying this for a while.
Oh, yes. These were incredibly important first steps in neuromorphic engineering, this whole field dedicated to designing hardware that mimics the brain's structure and function. But the real world is messy, extremely messy acoustically.
Echoes, noise.
Exactly. The complexity of real-world reverberant environments, think about an office with sound bouncing off every surface, or a busy street with multiple conversations and background noise, makes it incredibly difficult to achieve human-like accuracy. These early models often struggled with things like the cocktail party problem, trying to pick out one voice. But critically for localization, they struggled to distinguish the direct sound from its myriad reflections, its echoes.
Because the echoes would arrive later, messing up the timing and loudness cues.
Precisely. Echoes can utterly scramble those delicate ITD and ILD cues the system relies on. It's like trying to get an accurate time reading when your stopwatch keeps getting reset randomly by echoes. It just confuses the system.
Yeah. So the environment itself is a huge obstacle. What about the hardware side? You mentioned early systems face challenges there too.
Absolutely. That's been another major hurdle. Early analog chips trying to create these silicon Cochlea pairs and replicate the necessary delay lines, they often suffered from prohibitively large physical footprints.
Bulky chips.
Very bulky. Imagine trying to build those ITD-sensitive coincidence detectors
Hmm.
electronically. You need precise, finely tuned delay lines, essentially different length pathways for electrical signals to mimic the neural delays. Implementing these dedicated delay lines, which were necessary to capture those tiny time differences, required a lot of intricate circuitry and physical space on a chip.
Which means more power, more cost, less practical.
Exactly. They're bulky, power-hungry, and just not very practical for putting into the smaller, more efficient devices we need today. So the challenge has always been, how do you build something truly biologically inspired that is also compact, energy efficient, and robust enough to handle the chaos of real-world sound? And that's where this paper's approach comes in.
Okay, that sets the stage perfectly. We've got this incredible biological blueprint, but also these huge engineering hurdles, the noisy real world, the complexity of replicating delays in hardware. So how do you take this blueprint and turn it into something tangible, a practical silicon ear? Our source highlights a specific innovative model, the camera fix system. This sounds like the key innovation here, tackling those hardware challenges you just laid out.
It absolutely is, and it's really quite a clever piece of engineering in its design. The Carr-Feck model, which stands for Cascade of Asymmetric Resonators with Fast-Acting Compression, is a computational model specifically designed to emulate the intricate function of our own cochlea. Think of it as a silicon cochlea that doesn't just passively receive sound, but actively pre-processes it, preparing the signals for localization much like our own inner ear does, even before the brain really gets involved.
Okay, Carr-Feck. Let's break that down. What's the CR part?
Right, so the Cara part is the cascade of asymmetric resonators. This section brilliantly models the basilar membrane, the BM, in the inner ear. It consists of a cascade of special filters, two zero resonators, conceptually labeled H1 to HN in the paper. These are basically finely tuned filters where the center frequencies they respond to decrease progressively along the cascade. So one end responds to high frequencies, the other to low, just like the real basilar membrane.
Okay, so it splits the sound into frequency bands.
Exactly. But here's the truly innovative part, the real trick. As the sound signal travels through this cascade, each individual filter stage inherently adds a small, incredibly precise delay to the signal.
Ah, the delay is built in.
Yes. This inherent characteristic of the cascade structure is profoundly important. It provides a built-in distributed delay line. Remember how we said building dedicated delay lines was a major hardware headache?
Right, they were bulky and complex.
Well, here the delay isn't an add-on, it's fundamental to the filtering structure itself.
So instead of building a separate bulky delay line, they ingeniously baked the delay right into the structure that's filtering the sound anyway. That's incredibly efficient.
Yep.
Like getting two functions for the price of one component.
Exactly. It's a masterclass in efficient design. Then you have the FAC part, the fast-acting compression.
Okay, what does that do?
This is the crucial nonlinear component of the model, and it's what makes the Carr-Feck so remarkably robust to varying sound levels, mimicking the huge dynamic range of our own hearing. It includes several sophisticated submodels, a digital outer hair cell, DOHC model, a digital inner hair cell, DIHC model, and a multi-time scale automatic gain control, AGC.
So it adjusts the volume automatically.
In a very sophisticated way, yes. These components work together to provide adaptive compression. Just like our biological cochlea adapts instantly, so we aren't deafened by a loud noise, but can still hear a whisper, the FAC ensures the system doesn't get overloaded by loud sounds and remains sensitive to quiet ones. It maintains a broad, adaptable dynamic range, preserving crucial information across all sorts of sound levels. It's about handling real-world volume changes gracefully.
And there was one more part. Lateral something.
Right, good catch. After the DIHC output, there's a lateral inhibition, LI, block. This models the function of certain neurons in the cochlear nucleus. In the model, it's implemented quite simply with a discrete difference operation between adjacent frequency channels. Its main purpose is to effectively sharpen the temporal response of the system, making those delicate timing cues even more distinct and precise.
Like turning up the contrast on the sound signal.
That's a great analogy, yes. It helps highlight the edges and specific features of the sound's timing, refining the signal before it's used for the actual localization process.
So the Carr-Feck isn't just passively receiving sound, it's actively shaping, compressing, sharpening it. much like our own intricate cochlea does, before the signals even reach our brain.
Yeah.
That's a huge difference from simpler systems that might just filter the sound.
That's precisely the insight. It's doing a lot of the heavy lifting up front, really mimicking that biological pre-processing. And the real aha moment, again, is how the system cleverly exploits that inherent delay line built into the core cascade. Because each filter adds a tiny delay, the whole cascade forms this natural distributed delay line. The article points out that a 70-channel CARFAC, when responding to something complex like speech, shows an exponentially increasing delay along its channels, reaching a maximum delay of about 6.5 milliseconds.
And 6.5 milliseconds is enough delay range to cover typical human ITDs.
Oh yes, very much so. Typical human ITDs are usually under 1 millisecond, so this provides plenty of range. And this is just a brilliant engineering solution because it completely avoids needing those dedicated, physically large, complex hardware delay lines that older systems struggled with. The delay mechanism is intrinsically woven into the processing architecture itself. It simplifies the hardware, makes it way more compact, and significantly more energy efficient. It's just an elegant solution inspired by nature.
And for localization, naturally, we need 2 ears. So this system uses a binaural CARFAC setup, 2 of these modules working together.
Exactly. 2 independent FAC modules, one for each ear or microphone input, and the entire binaural CAR-FAC system, plus the next stage, which generates the correlograms we'll talk about, are all implemented on an Altera Cyclone V FPGA board for real-time processing.
FPGA, Field Programmable Gate Array. That means it's not just a simulation, it's running on actual reconfigurable hardware.
Precisely. The fact that it's running efficiently on an FPGA speaks volumes about its practicality. FPGAs offer this great balance between software flexibility and hardware speed and efficiency. This implementation means the PRFAC isn't just some theoretical model on a computer. It's a tangible step towards real-time, low-power, practical applications.
Making it suitable for embedding into actual devices, like robots or hearing aids.
That's the goal. It demonstrates genuine progress in making these biologically inspired systems not just effective in theory, but actually deployable in the real world.
Okay, so we've got these 2 sophisticated silicon ears pre-processing the sound, shaping and compressing it, just like our own cochleas, with that clever built-in delay. Now, the big question, how do these 2 ears actually talk to each other to figure out the sound's direction? This is where the correlogram comes in, you said. It sounds like we're moving from just hearing to actually seeing sound somehow.
That's a really good way to put it. To model the MSO's function, remember, the MSO in our brain compares signals from both ears to detect time differences. The system uses what's called coincidence detection computationally. Here's how it works. At any given moment, every frequency channel from the left CARFAX output is cross-correlated with all the frequency channels from the right CARFAX.
Every channel compared with every other channel.
Yeah.
That sounds computationally intensive.
It is. This generates a 2D instantaneous correlation matrix, which they call a correlogram. And this correlogram isn't just a jumble of numbers, it's a rich visual map. It effectively encodes both the interaural time difference and spectral information all in one snapshot.
So we're literally creating a visual map, almost like a dynamic heat map, showing how in sync or out of sync the sound is between the 2 ears, across different frequency bands simultaneously. That's a powerful way to see the ITD cues.
Exactly. You can literally visualize the timing differences. But you're right, doing that full cross-correlation is intensive. So to make this feasible for hardware, especially in FPGA, they introduced a very clever simplification: quantized instantaneous correlation.
Quantized, meaning simplified.
Yes. Instead of computing a precise numerical product for every single cross-correlation point, which requires multiplication, a relatively expensive operation in hardware, the correlation is ingeniously quantized into a binary range. It's simplified to either +1 if the product of the 2 channel outputs is positive, meaning they're correlated or in phase, or -1 if the product is negative, meaning they're anti-correlated or out of phase.
So just a simple plus or minus 1.
Yeah.
Instead of a detailed correlation value.
Precisely. This binary simplification is a game changer for hardware. It drastically reduces the computational resources needed. No complex multipliers, just simple comparisons and sign checks. The paper notes really impressive device utilization figures on the FPGA. Adaptive logic modules, ALMs, at 52%, memory at 40%, and digital signal processors, DSPs, at 92%. These numbers show it's a highly optimized design, fitting efficiently onto the chip.
That makes sense. It's a trade-off, right? Simplify the representation and make it practical.
Exactly. It highlights a crucial principle in neuromorphic engineering. Sometimes, simplifying the information representation can lead to highly practical, efficient systems without a significant loss in performance. Finding that sweet spot is key.
That's a really important insight. So let's make these correlograms concrete. What do these sound fingerprints actually look like? How do they visually represent these timing differences for different sounds?
Okay, yeah, visualizing them helps a lot. Imagine this grid, right? One axis is the frequency channels from the left ear. The other axis is the frequency channels from the right ear. Now, for a simple case, zero delay sine tones, let's say a pure 200 hertz tone hitting both ears at exactly the same time. The correlogram shows this beautiful symmetric pattern right along the main diagonal.
The diagonal means left and right channels at the same frequency.
Right. And you also see these distinct off-diagonal stripes, alternating white correlation +1 and black anti-correlation -1. These stripes appear because of the phase shifts that naturally occur across the different frequency channels of the psi-R cascade itself.
Okay, so identical sounds give a symmetric pattern. What if there's a delay?
Ah, that's where it gets visually informative. If one signal is delayed, say simulating a sound coming from one side, the correlogram visibly changes. That strong correlation stripe that was on the diagonal, it shifts off the diagonal towards the side corresponding to the delayed Cochlea, and the off-diagonal patterns become asymmetric.
So the shift directly shows the delay.
Yes. The amount of that shift off the diagonal is a direct quantifiable measure of the ITD. You can literally see how much later the sound arrived at one ear. It's like a visual gauge for sound direction.
That's incredibly clear. What about more complex sounds, not just simple tones?
Good question. With two-tone inputs, say 800 hertz and 1200 hertz played together, the correlogram naturally shows strong activations, bright spots at both those frequencies along the diagonal. Makes sense. But here's where the nonlinear nature of the Carfax, specifically the FSC part, really shows its biological fidelity. You see an additional activation appear, a fainter one, at 400 hertz.
400 hertz. But that wasn't in the input sound.
Exactly. This represents a cubic difference tone, or CDT. This is a known psychoacoustic phenomenon. Our own ears generate these phantom tones due to nonlinearities in the cochlea.
So the model is actually generating the same kind of auditory artifact as our ears.
Precisely. Its appearance here shows the Carfax isn't just filtering, it's truly emulating a complex biological function of the cochlea. This CDT is notably absent if you just use the linear car part without the FAC compression. It really highlights the FAC's contribution.
That's fascinating. What about noisy sounds like white noise?
For broadband signals like white noise, which has energy across all frequencies, its correlogram at zero delay shows strong energy along the diagonal, as expected. But the off-diagonal patterns are less organized compared to pure tones because noise lacks those regular phase relationships. However, introduce a delay to the white noise, and that central energy band clearly bends or curves towards the delayed side. So even for complex diffuse noise, the correlogram still visually indicates the ITD.
These really are like sound fingerprints. But the crucial test is speech, right? And speech and noise.
That's the ultimate test, yes. And this is where the correlograms truly reveal their power. Speech signals produce very distinctive correlograms. You still see energy along the diagonal, but crucially, you also see distinct off-diagonal stripes. These are a direct result of formants, the resonant frequencies of our vocal tract that shape vowel sounds.
Ah, the formants.
Yes. As speech travels through the Carfax channels, these formants create regular in-phase and counter-phase delays across specific frequency channels, forming those characteristic visible stripes. It's like a combined spectral and temporal fingerprint of the speech itself.
So it contains info about direction and the speech content itself.
Potentially, yes. And this leads us to speech in noisy environments. This is critical. The research shows the system can actually start to differentiate between sound sources. They tested combining speech with zero delay with white noise that was delayed. The resulting correlogram clearly showed symmetric patterns for the speech components, often in lower mid-frequency regions, and separately, distinct delayed patterns for the noise components, often stronger in higher frequencies.
So you could visually see the speech pattern centered and the noise pattern shifted.
Yes. This visual separation within the correlogram is remarkable. It strongly suggests the system has an intrinsic ability to begin segregating sound sources.
Which is a huge deal. That's moving towards solving the cocktail party problem.
Exactly. It opens up possibilities far beyond just knowing where a sound is to understanding what the sounds are, even when they're mixed together. That's a massive step.
Okay, those correlograms are incredible detailed visual maps of binaural cues, potentially separating speech from noise. But a map isn't quite a direction yet. How do we translate these complex visual maps into a precise angle? And crucially, what about those echoes we talked about? How does the system avoid being confused by reflections bouncing around a real room? That seemed like a killer problem for earlier systems.
You've hit on maybe the most critical point for real-world use. Dealing with echoes or reverberation is absolutely paramount. Our own human auditory system has this really clever mechanism called the precedence effect. It basically means we tend to localize a sound based on its very first arrival, the direct sound, and we largely ignore subsequent echoes that arrive shortly after, say up to 40 milliseconds later.
So our brain prioritizes the first sound wave it hears.
Essentially, yes. It prevents us from perceiving a confusing mess of echoes as separate sound sources. Without it, every room would sound like a confusing echo chamber.
Okay, so does the system mimic that precedence effect?
It does in an inspired way. The system incorporates a sophisticated onset detection algorithm. This algorithm is constantly listening, continuously calculating the logarithmic change in input energy over a short time window. If this energy change suddenly jumps up, exceeding a predefined threshold, an onset is detected. This signals the likely start of a new, distinct sound event, hopefully, the direct sound arriving.
It's listening for the sound to start.
Exactly. It's trying to capture that crucial initial wavefront before the room's echoes have a chance to arrive and muddy the waters.
That's brilliant. It's like the system learned to filter out reverberation by focusing on the beginning of the sound, just like our brains instinctively do. Okay, so it detects an onset. We get a clean, echo-reduced corellogram that refines sound fingerprint. What happens next to get the actual angle?
Right, so once an onset is detected, the system generates what's called the onset corellogram. This isn't just any instantaneous corellogram. It's specifically created by averaging the instantaneous corellograms over a short, critical period immediately following that detected onset. In the experiments, they used about 90 milliseconds.
The averaging after the sound starts.
Yes, this targeted averaging dramatically decreases the influence of those later arriving echoes by focusing intently on the very start of the sound, capturing the characteristics of the direct wave. It ensures the localization decision is primarily based on that initial, cleaner signal. It's a very clever computational way to emulate the precedence effect.
Okay, makes sense. So now we have this clean, onset-focused corellogram. How does that become an angle?
This is where machine learning comes in. These refined onset corellograms are then fed into different types of regression neural networks. These networks are trained specifically to learn the complex patterns within these 2D corellogram maps, and from those patterns, predict the azimuthal angle, the horizontal direction of the sound source.
So the network learns to read the map and output a direction.
Precisely. The researchers investigated several different machine learning approaches to see which worked best. First, they used simple linear regression. This served as a basic baseline model, a kind of how well can we do with the simplest possible approach? Sanity check. It helps quantify the benefit of more complex networks.
Okay, a starting point.
Then they tested an extreme learning machine, or ELM. ELMs are interesting. They're a type of feed-forward neural network known for learning very fast and often generalizing well to new data.
Faster learning.
Because their hidden layer weights are just randomly assigned and then fixed, only the output weights are trained. It simplifies the training process significantly. And importantly, as the paper notes, ELMs can potentially be implemented efficiently on FPGAs. This means the entire system, CRFAC, pre-processing, corellogram generation, and the ELM prediction could eventually run entirely in compact hardware.
Ah, that's a big deal for embedded systems. Real-time, low power.
Exactly. That's a major potential advantage.
And then I assume they brought out the big guns, the deep learning models.
You guessed it. Finally, they employed a convolutional neural network, or CNN.
Like the ones used for image recognition?
Exactly the same principle. Deep CNNs are state-of-the-art for tasks involving spatial data, like images. And given that these corellograms are fundamentally 2D visual representations, these sound fingerprints, CNNs are incredibly well-suited to extracting the important spatial features, the subtle patterns, the shifts off the diagonal, the shapes of the stripes, all the things that indicate direction. The specific CNN architecture they used had 2 convolutional layers, 2 pooling layers, a fully connected layer, and an output layer, all carefully configured through experimentation for the best performance on this specific regression task of predicting the angle.
Wow. So it's this combination, biologically inspired pre-processing with the CAR-FANG, That's smart echo suppression using onset detection inspired by the precedence effect, and then the pattern recognition power of deep learning algorithms like CNNs. That really sounds like a recipe for robust sound localization.
It absolutely is. It's a fantastic fusion of insights from biology, clever signal processing, and cutting-edge AI, all focused on this one challenging goal.
Which brings us to the critical question you raised earlier. How well does it actually work? Especially that CNN model. How did it perform in the real world, with messy speech and echoes? And crucially, how does it compare to us humans?
Right, that's the million-dollar question. Performance is everything.
Theory is one thing, fascinating as it is, but yeah, real-world performance is the ultimate test. How did they set up the experiment? What kind of environment, sounds, and what were the key takeaways?
Okay, so the experimental setup was designed with real-world relevance firmly in mind. They deliberately avoided a perfect, soundproof anechoic chamber. Instead, binaural speech data was collected in a reverberant office environment.
A regular office with desks, walls, windows, echoes.
Exactly. This choice is crucial because it means the results are directly relevant to everyday scenarios where echoes and background noise are just part of life. They were testing it in the wild, so to speak. For the physical setup, they used two high-fidelity microphones placed zero point 0.4 meters apart on the floor.
Why zero point 0.4 meters? That's wider than human ears.
Good point. It is wider. This wider spacing actually increases the maximum ITD produced, making the time differences larger and potentially easier for the system to measure accurately within its 6.5 meters range. A speaker playing the sounds was positioned 0.96 meters away from the center point between the mics. This specific geometry created a maximum possible interval time difference in their setup of about 1.17 milliseconds, well within the system's capabilities.
Okay, so the setup was designed to give clear, measurable cues within the system's range. What sounds did they play? Simple tones?
No, definitely not. They used 10 isolated spoken digits, 0 through 9, recorded by 5 different speakers, both male and female, taken from the Austalk database.
Austalk. That's a database of Australian English speakers.
That's right. Using natural, complex human speech from multiple speakers is vital. It makes the test much more realistic and challenging than using simple, predictable tones. And these spoken digits were played from 13 different locations, 13 different azimuthal angles, sweeping from -90 degrees, hard left, all the way to +90 degrees, hard right, in precise 15-degree steps.
Covering the whole frontal arc.
Exactly. A very comprehensive test of directional accuracy. And to make the system even more robust, they used data augmentation. They artificially expanded the training dataset by adding band-limited noise at various signal-to-noise ratios, between 15 and 25 dBFS.
Simulating different levels of background noise.
Precisely. They even inverted signal values. This whole process resulted in a much larger dataset, over 11,700 samples, giving the neural networks plenty of varied examples to learn from, making them more resilient to noise and variations.
That sounds incredibly thorough. Real speech, real reverberant room, multiple angles, added noise, lots of data. Okay, so the moment of truth.
Oh.
What did the results show? How did the different networks, linear, ELM, CNN, compare?
The results were stark and really compelling. The convolutional neural network, CNN, significantly outperformed both the linear regression and the extreme learning machine, ELM. Linear regression, as you'd expect, had pretty large errors and variations. The ELM was definitely an improvement, showing faster learning potential too. But the CNN's predictions were consistently the closest match to the actual sound source locations across all angles.
So the CNN was just much better at reading those complex correlogram maps.
Essentially, yes. It demonstrated a superior ability to extract those crucial, subtle features and patterns from the noisy correlograms, leading to much more precise and reliable localization. It just had a much better eye for the details in those sound fingerprints.
Okay, that makes sense. CNNs are good at pattern recognition. But you mentioned something surprising earlier about the linear car model versus the nonlinear car FAC.
Yes, that was one of the really fascinating findings, with big implications for hardware design. Counterintuitively, when they compared the full nonlinear car fake model with a simpler linear SCAR model, so without the fast-acting compression part, the linear SAR model actually showed slightly smaller averaged unsigned errors.
Smaller errors with the simpler model. How can that be?
It suggests that for these specific test conditions, which were relatively high signal-to-noise ratio, even with the added noise, the extra complexity of the FAC's nonlinearity wasn't actually providing a benefit for localization accuracy. It might even have added a tiny bit of unhelpful distortion or variability in this context.
So for this task, under these conditions, The complex compression wasn't needed.
It seems not, and this is crucial. It means you could potentially build a simpler linear CAR-based system that uses less computational power and less energy, and still achieve top-notch localization accuracy, at least in reasonably clear conditions. That's a huge win for practical engineering. Sometimes simpler is better, or at least just as good.
That is a surprising and really valuable finding. Okay, what about the other simplification? The quantized correlograms. The binary plus minus one thing. Did that hurt performance?
That was the other really surprising and incredibly positive result. The performance using the quantized correlograms was remarkably close to using the full non-quantized versions.
Even with just plus one and maybe one.
Even with just +1 and -1, there were only slightly larger standard deviations in the errors, mainly at the extreme side angles like 90 degrees, where localization is inherently harder anyway.
Wow. So that huge computational saving comes at almost no cost in accuracy.
Pretty much. It's a massive win for practical hardware implementation. It proves you can dramatically reduce the computational load, the power needs, the chip space, without a significant hit to accuracy. That makes putting this kind of tech into real devices much, much more feasible. They also tested a few other things, like the center frequency, CF range used wide versus narrow, and the input type fed to the CNN. Example, using the whole corellogram versus just a diagonal region. Interestingly, while the narrower, higher frequency range, 500 Hz, Satus 8 kilograms, correlograms, looked visually cleaner, the CNN performed well with both ranges. And focusing the CNN's input on just the diagonal corellogram region where the ITD cues are strongest often gave slightly smaller errors.
Suggesting focusing the network on the most relevant data can be beneficial.
Exactly. Smart input selection matters.
Okay, so we have a system, particularly the linear CR, paired with the CNN using quantized correlograms, that's efficient and highly accurate in a realistic test. But the big question remains, how does it stack up against us, against human performance?
This is the truly pivotal comparison, and the answer is quite stunning. The proposed system, CRR pair, quantized correlograms, CNN predictor achieved root mean square, RMS errors of about 2.8 degrees for angles in front, 0.45 degrees, and about 4.3 degrees for angles to the side, 45-90 degrees. If we look at unsigned average errors, which is how human performance is often measured, the system got about 1.3 degrees in front and 2.9 degrees to the side.
Okay, and humans. What are typical human errors in similar tests?
Well, studies on human listeners in similar reverberant conditions, localizing speech, typically report unsigned average errors of around 4 degrees in front and maybe 7 degrees to the side.
Wait, repeat those numbers.
Yeah.
The system got 1.3 and 2.9 degrees. Humans average 4 and 7 degrees.
That's right.
So the machine was more accurate than the average human listener in this specific test.
In this specific evaluation, using natural speech in a reverberant office environment, this biologically inspired system, especially with the CNN, did indeed demonstrate localization accuracy that surpasses average human performance.
That's incredible. Genuinely incredible. A machine learning to hear location better than we do in a real-world setting, it really highlights the power of combining that biological inspiration with smart engineering and powerful AI.
It's a remarkable achievement, definitely. It shows the potential of this approach.
Wow. Okay. So what does this all mean then? We have a system that's biologically inspired, computationally efficient, and can localize speech in a tricky environment with accuracy that, frankly, blows my mind by beating human averages. Where do we go from here? What are the big takeaways and future possibilities?
Well, the core conclusion is really impactful for the field. It shows that, at least in relatively high signal-to-noise conditions, you can get robust, highly accurate sound localization using a linear SciR model combined with those efficient quantized 2D correlograms and a well-trained CNN. And the fact that the simpler linear SciR model performed so well is hugely significant. It points towards practical applications with less hardware complexity, lower power consumption, making it feasible for real devices.
Right. Efficiency is key for real-world tech.
Absolutely. And the researchers also discussed potential improvements. For instance, they suggested extending the 70-channel CRFAC model to maybe 100 or more channels.
Why more channels?
More channels could potentially increase the ITD detection range even further, maybe allowing for even finer angular resolution or handling wider microphone spacings. They also suggested adding a threshold during the quantization step, maybe ignoring very weak correlations, which could further decrease noise sensitivity and improve performance in even noisier environments than they tested.
So pushing the boundaries into even tougher conditions.
Exactly, constantly refining and improving.
But beyond just localization, pinpointing direction, the paper hinted at some really exciting, broader applications for this tech.
Yeah.
What else could these sound fingerprints, these correlograms, be used for? They seem packed with information.
Indeed. The potential goes way beyond just where. Since the correlograms, as we saw, effectively encode the formants of speech, those characteristic frequency patterns the system's pre-processing and the rich data in the correlograms could be directly leveraged to significantly enhance speech recognition systems.
How so?
Imagine a voice assistant that doesn't just rely on the raw audio. It uses this Carfax pre-processing and correlogram analysis to get a much richer, cleaner representation of the speech, maybe even separating your voice from background noise before trying to understand the words. This could lead to much more accurate recognition, especially in noisy places.
So better understanding what is said, not just where it's from.
Precisely. And furthermore, remember how the system could visually differentiate between speech and noise patterns in the correlogram, that distinct visual separation?
Yeah, the speech pattern centered, the noise pattern shifted.
That opens up profound possibilities for sound source segregation, actually unmixing sounds.
Like the cocktail party problem again.
Exactly. Imagine a system that can intelligently unmix multiple sounds happening at the same time, isolating a specific conversation from background music, traffic noise, other people talking.
The applications for that are huge. Hearing aids.
Transformative for assistive listening devices. Imagine a hearing aid that doesn't just amplify everything, but uses this tech to isolate the voice of the person you're talking to, suppressing everything else. That would be life-changing for many people.
Or robots needing to understand complex environments.
Definitely. Advanced robotics operating in busy, noisy places. A rescue drone needing to pinpoint a faint cry for help amidst storm noise. A self-driving car needing to instantly identify and locate an ambulance siren in dense city traffic. This moves beyond just hearing to truly understanding the composition of the sound world.
The idea of machines not just hearing, but intelligently processing, segregating, and understanding the entire soundscape around them with a precision that can even surpass our own. It's truly mind-blowing. The potential for smarter, more intuitive human-computer interaction, for safer autonomous systems, for better accessibility, it's immense.
It really does raise a fascinating question, doesn't it? If we can achieve this level of accuracy and efficiency by mimicking biology, what are the ultimate limits here? How might these advancements fundamentally change how we design the next generation of sensory tech, and maybe even how we think about artificial perception itself?
Yeah, it feels like we're on the cusp of something really big in how machines perceive the world through sound.
It's certainly a very exciting time in neuromorphic audio engineering.
What an incredible journey we've taken today. Seriously. We started by marveling at the sheer elegance of how we locate sound, got into the nuts and bolts of the silicon cochlea, the CRFA, with its clever built-in delays. Explored that visual language of correlograms, these amazing sound fingerprints, saw how smart onset detection helps beat echoes, and then how powerful CNNs can learn to read those maps with superhuman accuracy, all proven in a real-world test.
The ingenuity is really something. Leveraging the CRL model's inherent properties, simplifying the data massively with quantization but keeping the accuracy, and then applying state-of-the-art AI, it just underscores the incredible progress in neuromorphic engineering. It's about building intelligence right into the hardware's fabric, making systems that are not just powerful, but efficient and robust enough for the real world.
So here's a final thought for you, our listener, to mull over. Imagine a future where your smart devices don't just vaguely hear sound, but truly understand where it's coming from, who is speaking, maybe even separate individual sounds in a crowded room, just like you instinctively try to do. How might that fundamentally change how you interact with technology? How might it change the world around you? Think about truly safer self-driving cars, way more immersive virtual realities, or hearing aids that finally let people hear exactly what they want to hear in noisy situations. The soundscape of our future is definitely about to get a whole lot smarter. Thank you so much for joining us on this deep dive into biologically inspired sound localization. We hope you leave feeling a little more informed, definitely a lot more curious, and maybe just a bit more amazed by the intricate symphony of sound that constantly surrounds us all.